right, problem 4. We are going to find the volume of the solid obtained by rotating the following region about the y-axis. Okay, so our region is in the first quadrant, bounded on the left by the circle x squared plus y squared equals 3. Okay, so this is a circle with a radius of square root 3. All right, because x squared plus y squared equals r squared. Remember that good little thing. Okay, let me make my first quadrant here. X, y, okay. So our circle has a radius of root 3. Root 3, root 3, and I'm going to try and make a circular shape between those, or at least a quarter of a circle since we're just looking at the first quadrant. All right, circular curve like so. And then our region is bounded on the right by the line x equals square root of 3. Okay, how convenient. That is right here. And then our region is bounded above by the line y equals square root of 3, which would come in right here. Okay, so where those three graphs intersect, the area bounded between them is the area that we're going to rotate. So that would be this part right in here. All right. So we're going to take that region and we're going to rotate about the y-axis. So rotating like so. Imagine this coming out of the computer, rotating around. It runs into your computer screen again over here, making kind of like a mirror image type of shape. All right. And then it continues back around behind the computer screen until it makes the full circle. Okay. And so our solid, anyone want to describe this one? What this one is going to look like? There's no wrong answers to these, really. Yeah, I like Brandon's description there. It's like a boxed bowl. So yeah, it's like a bowl, but with these square boxy outsides. Yeah, kind of an interesting bowl design, really. So yeah, were Felipe there a box with a bowl mold? Yeah, like maybe something a ceramics artist would use to cast bowls, perhaps. Yeah, it would have these straight cylindrical outsides like this. And then the inside of it would be kind of cut out in a bowl shape. So this is what the outside of the shape would look like. And then inside you'd have that kind of scooped out of the middle circular bowl part. Okay. So on this, we want to look for our outer radius here and our inner radius, because this obviously has a hole in it. It's going to be a washer type of shape. So our outer radius goes all the way to the outside, and then our inner radius goes from the center to the cutout portion. Okay. And we can also see here, if we want to get the nice circular cross sections, we are going to need to slice this horizontally, like this. Okay. Yeah, otherwise, you know, our method here would not work. You can also figure that out by seeing that we're going about the y-axis. So we're going to need to slice little changes in the y, and we're going to do everything with respect to y here. So, yep, slice like so. And so, yeah, our slice would be a washer shape. All right. So let's imagine this slice here. And imagine taking that slice from somewhere that actually has a hole to it. The very, very top of this is actually a solid, but as soon as you get anywhere below that, it's just like so thin at this point right here, but then anywhere below that, there's solid and like an actual hole. So just saying. All right, so here again, that is the little inside radius, and then going all the way to the outer edge, that would be the big radius, big R there. Okay. So we've got also our thickness or height here, and that is definitely going to be a delta Y expression. So yeah, here we've got H equals delta Y, adding up all these little slices in the Y direction. What is the outer radius of this? What's the big radius?
Is it the square root of 3?
It is, yeah, and it's the same thing all the way down. That's good. Because yeah, since our object here has this straight outer edge that's just given by the line x equals square root of 3, that outer radius is the same every single time for every single slice. So there's the outer radius, there's the outer radius. My little swooshies are getting worse, but there's the outer radius. Those are getting wacky, but every single time the outer radius goes to that purple line, x equals square root of 3. So spot on, Natalie, you got it. So square root of 3. All right, it's a constant outer radius. And then what gives us our inner radius? Our little cutout portion. Hint, that one's not going to be a constant. Inner radius here is changing as we move through different y values.
Would that have to do with the x squared plus y squared equals 3?
Yeah, very good. It sure would. So yeah, the inner radius is determined by the circle. So yeah, that is the x squared plus y squared equals 3 for sure. But yeah, here, since we've chosen to do like delta y, we're going to have to put everything in terms of y. So we want this as a function of y. So it would be, if you solve that equation for x, then y would be your variable that everything is in terms of. So that would be x squared equals 3 minus y squared. And so then we'd square root both sides and get x equals square root of 3 minus y squared. And remember not to apply that square root to the y squared. This is not root 3 minus y. It's just square root of 3 minus y squared. But yeah, that is a function of y now. So we can use that for our inner radius. So yeah, we did need to use the circle there. All right, so that gives us our little r. All right. And we'll set up our delta v expression. Pi big R squared minus little r squared. And then h. Yeah. And that would be pi. And then here our big R is square root 3. And then that's getting squared. And then our little r is square root of 3 minus y squared. So there's little r squared. And then h is delta y. So there's definitely some stuff we can simplify there. A lot of square roots getting squared. Okay, so we're going to have pi, and then 3 minus, and here the square root would go away, so 3 minus y squared, delta y. And yeah, the 3's actually cancel out for us, so that's fantastic. Okay, so we get pi, y squared, delta y. And yeah, that one's not going to be too bad to integrate. Let's check our limits for that integral as well. So what are our limits on this?
0 to square root of 3.
Yep, exactly. So y equals 0 to square root of 3, because we're going to add up these y slices all the way from the bottom, 0, all the way up to square root of 3 up top there. So yeah, but that's what we're doing. And so yeah, our integral, oops, square root of 3. Our integral for v is going to go from y equals 0 to the square root of 3. And you pop your delta v expression in there, pi y squared, and delta y becomes dy. Okay. And then we will finish that up by integrating it. So take your antiderivative. This one's pretty quick. We'll just plug in those limits here. 1/3 times the square root of 3 cubed minus 1/3 times 0 cubed. How nice that we keep getting to plug in 0. That is sweet. So we get pi, and then that would be 1/3, and then the square root of 3 getting cubed is 3 root 3, because square root of 3 squared would give you the 3 portion, and then there's another root 3 on there. So yeah, the 1/3 and 3 actually cancel out, and we end up getting pi square root of 3 cubic units for our answer. So that's the volume of this shape, this boxy bowl thing.